When you look at the sun, what do you see? Probably a giant, chaotic ball of fire, right? A place of just pure, wild energy. But what if I told you that underneath all that chaos, there is a hidden rulebook, a secret set of laws that's actually running the whole show? And that's exactly what we're going to get into. Scientists are finding that the sunspots that pop up all over the sun's surface, which seem totally random, actually follow a surprisingly predictable set of rules. And here's the really cool part. It's the sunspots that break those rules that are teaching us the most. So let's meet the main character in our story, the solar active region, or AR for short. These aren't just little dark spots. Oh no. They are massive, supercharged magnetic hotspots where energy from deep inside the sun literally bursts through to the surface. For scientists trying to figure out the sun, these guys are everything. Okay, so if you want to find the hidden rules, you first have to figure out how to read the blueprints, right? Scientists had to measure and categorize thousands of these active regions, basically creating a massive database of solar behavior. Think of it like a stat sheet for a sunspot. For every single one, scientists track 4 key things. You've got its magnetic power, called flux, its physical size, the area, the distance between its own little north and south magnetic poles, and finally, its tilt angle, basically how it's sitting on the sun's surface. And when you track these 4 stats across thousands of sunspots, patterns start to jump out. So, what did they find? Well, first up, a pretty simple rule. The more magnetic juice a sunspot has, the bigger it gets. It's that direct. You can see on this chart how all that data just lines up. And what's really neat is that the newer theory, that's the orange line, it hugs the real-world data way better than the older idea, the green line. It's a perfect example of how science is always getting sharper. And rule number 2 is just as clear. More magnetic power doesn't just make the sunspot bigger, it also pushes its north and south poles farther apart. And again, just look at that orange line. It tracks the real data almost perfectly. It's like we're finding the sun's hidden blueprint. A little bit of order is starting to form out of all that chaos. But it's not just about size and power. The next piece of the puzzle is all about orientation. How are these massive magnetic things actually aligned on the sun's surface? And this brings us to a huge rule in solar physics called Joy's law. Basically, it says that these active regions aren't lined up perfectly east-west. Nope, they're tilted. The part that's leading as the sun rotates always sits a little closer to the equator. You can kind of think of it like a tilted compass, and how much it tilts depends on where you are on the sun. And would you look at that? The data backs it up perfectly. This chart is so cool. It shows that as you move away from the solar equator, the average tilt of these sunspots just increases in a straight, predictable line. It's this beautiful, simple rule written right across the face of the sun. But here's where it gets kind of mind-bending. Joy's law is just an average, right? Some sunspots stray from that line. But get this, scientists found that even the messiness isn't random. These charts show that the bigger and more powerful a sunspot is, the less it strays from the rule. It's like the real heavyweights on the sun are just better at following the law. So even the exceptions have their own rule. Incredible. So we've got these really elegant rules for size, shape, and tilt. We're starting to feel like we've got the sun figured out. But of course, just then, we discover that some of these active regions are complete and total rule breakers. About 5% of them. Now that might not sound like a lot, but it's a huge chunk of all the active regions we see. These are the rebels, and they break the most fundamental magnetic rule of all. Scientists have a technical name for them, non-Hale regions. We're just going to call them rebels. And what makes them rebels is that their magnetic polarity is completely backward for where they are. Their internal compass is pointing the wrong way. And for a long, long time, nobody could figure out why. And the mystery only got deeper when scientists looked closer. This chart shows the tilt angles for just the rebel sunspots. And what is that? Look at that huge, totally unexplained spike right at the very low tilt angles. They're almost perfectly aligned east to west. These became known as the anti-Hale rebels. What on earth were they? And this is the smoking gun. When scientists plotted only those weird anti-Hale rebels, they must have been shocked. That orange line, that's Joy's law. That's where they should be. But the rebels, they're scattered everywhere. And their average tilt is just a flat line at 0. It doesn't matter where they are on the sun. They don't just bend the law, they are playing a completely different game. This discovery just demanded a whole new explanation. How could a small group of sunspots behave so differently when they look pretty much normal otherwise? Well, the answer, as it turns out, is beautifully simple and just a little bit violent. The researchers who figured this out put it best. They said the best explanation is that these rebels aren't a different type of sunspot. They're just normal sunspots that got subjected to extreme intermittent torques. In other words, as they were rising to the surface, something grabbed them and twisted them violently. And this is what they call the twisted loop theory. It's brilliant. It goes like this. A normal magnetic group starts rising up from way down inside the sun, but on its way up, whoops, it gets caught in a giant churning whirlpool of plasma. This vortex twists the loop hard. If it gets twisted past 90 degrees, its magnetic poles flip. Bam, you've got a rebel. And if it gets twisted almost a full 180 degrees, it pops out as one of those flat, mysterious, anti-Hale rebels. And this simple idea also explains that weird pileup we saw in the data. I mean, why are there so many rebels twisted to almost exactly 180 degrees? Well, it's just basic physics. As you twist that magnetic loop that far, its two legs literally start bumping into each other. That creates resistance, making it way harder to twist any further. So the loops that get caught in these vortices just tend to get stuck or pile up at that 180-degree orientation. It just makes sense. So, what's the big takeaway from all this? Well, by focusing on the 5% of sunspots that break the rules, we end up understanding the other 95% way better. This whole twisted loop idea helps scientists build much more accurate models of the sun's magnetic engine. And that is absolutely vital for predicting things like solar flares and protecting all of our technology from what they call a stormy space climate. It's just such a powerful reminder that sometimes in science, the biggest breakthroughs aren't in the neat and tidy data that fits your theory perfectly. No, sometimes they're hidden in the messy, rebellious outliers that just refuse to follow the rules. It really makes you wonder, doesn't it? What other huge secrets about our universe are just sitting there, waiting for us to find them in the exceptions?